Okay, because we're going to continue right on this topic, space-time. And when I go say talk about space-time, I'm talking about space-time, time-space. Really, they're the same thing. You're talking about the stone dock is mathematics in this space, in this conversation, at this time. Absolutely. In other times, talking about time spaces, it might be different. That's a fourth dimensional calculation, a spectrum problem, a general relativity problem, a photon through the Earth and around the Earth. They're both very different equations. And in one given space, talking about the photon around the Earth, where that math equation is going to look very different than the one that's traveling straight through the Earth. Just a problem I use to describe it. And you can break it down. It's not that you couldn't run infinitely with a number of billions of different problems, because it still applies to the flaw variable. But how far can you make it run? You're the one behind the handle on the wheels. You could be like, well, one's faster than the other. They equal at the same time. I'm sure. Absolutely, both are the right answers. Now prove it. Now go out there and lead with it, is what I'm going to tell you. And take it to the next level. Be a math teacher about it. Well, I don't want to do all that responsible. I'm going to fucking swat you, Murphy. God damn it. Learn! Direct physics, which again is going to cover a lot of material in base physics. Now, hopefully, we're going to see the jump here. We're talking about really heavy-duty mathematics on the other side. And on this side of the equation, just because it was the given space that I had, and I had to do them all in the same amount of time with the same number of numbers, that they made a kind of a quantum leap. And we're talking about the way they're reciprocating. A lot of mathematics that will help you make forms and make examples, which is very direct to the need that you want to do. And we're going to say that that's physics, but it's psychology, it's trigonometry, it's algebra. It's all under one hat of direct physics, creating that as a general to say, this is the class I've created. It's not applied physics. We're not going to take all those equations out there and do this. We're taking some of the stuff that's hard to see and lay it all out. Here's the X, Y's, and Z's that we create for this specific second, because not all that physics equation is going to apply. It might after it's all created, but until it is, I got to start making things direct. I got to be like, lay down some orders and force my ass to get up in the morning and fucking lay it down. That's what you got to do. Chimeric viscosity. When you think about this, I have this as K, in parentheses, apostrophe V, irrational number PR. We're talking about chimeric viscosity in its velocity of the irrational number of pressures and resistances, is how I like to describe this. And they're stacked. Sometimes there's a lot of time problems, monetary problems, and this will help. We're going to cover this, but it's helping you teach, again, just reciprocating. Direct physics, be applied, make models, do analyzation, run hypotheses. Do you have time to do those things? What kind of system do you have? Because all of those models kind of going together. And not that this one course will get you there, but the practice of this model is your viscosity. This is what's slowing you down to, oh, that stuff is real. That stuff does make sense. That stuff does apply into a lot of conversations. And it'll help you make that a little quicker as well. And when you do that a little bit quicker, which is you're just percentageably making yourself a little better at all times, it's going to take off some of that pressure. It's going to make the viscosity a little bit more like water than oil. Be like water, Bruce Lee, is how I like to talk about it. You got to flow. The stuff, it exists. Now, can you make it flow in quantum gravities like general relativity, the equation Einstein laid out that made sense to a lot of people, and they can make it flow in general? Again, not all the features, but well enough to break it down to the physical level, where physics equations, the laws of motion, Ohm's law, hydraulic systems and mathematics that go along with hydraulics and valve reductions actually make sense. Chimeric viscosity. Biometrics. which again, this is talking about, physics. This is talking about human physics, the human body, your time systems, your physical development. Are you tracking these things? Are you tracking not only the time systems that I go into the saw, but are you getting stronger? Are you eating right? Are you doing all those things? Because all this applies in direct physics. All this applies in A mechanics. They're all the same system. They just look very different, and they're taught to be totally different models, and that's just not the truth. They're all the same thing, and if you can tap into this kind of thinking, A mechanics and direct physics, you should be able to tap into all of them. And it should be almost intuitive to how fast you learn these things, or how fast you adapt them to your needs. Beyond that, there's the internet. Look shit up. A equations, which are a lot of equations that are out there, and can you create new equations? Can you condense old equations into new forms, and what have you? Which go into face equations. Face. Whether you believe this is the face of God, or how I reference equations to directly the things that I'm breaking down. The stone dock, it's got rotational forces, flow of water over the saw, diversified inconsistency equations of these general numbers, of the law of diminishing exchange, and also special relativity to say these specific numbers. They're the face equations you need to learn how to write. Get good with it. Power series, which is a math equation. How you look at it here is going to help you tap into. It's going to say tap into IN, irrational end state 2. Squaring platforms is how I like to talk about it. And I forget exactly what that equation looks like, but once you get good, and I have all this stuff written down for you, I'll walk you through the equation. You'll be like, oh wow, that stuff is real. Here's a stone dock. Here's this aspect of it. Here's when you start to work it down, it's falling away from zero to smaller features. All are equal in size to being infinity states, to being a point of power. But that's what the design of that equation helps you understand what that is. And if you understand some of those symbols by how they're generally formed, who brought them to the table, how it was laid out, what's the major area that they talk about that stuff. It's not just electricity, it's not just physics, it's all kinds of things. So we're learning that a lot of these equations have the same power inside of them. Not only are they equal but opposite, but sometimes the force, when you look at them, is a zero state field of power series, creating a flow of circuitry engineering inside of this idea. Number theory. And again, we're talking about all different equations, physics, algebra, trigonometry, and we're just saying, well, these are theories to help you understand some common sense shit that's right in front of you, to help you lay out those numbers, help you test it, help you do it a little quicker than a million times trial and error, to reduce it down to a prime system, where and when all of those different 3, 5, 7, 11 are the only time. What makes them what they are, and then giving it a definition to all those other conversations, and inverted highly composite systems, which is another prime model of. The higher the number system you go, usually they're more composite, more mathematical features that'll make them prime again, or whatever. They multiply this and this, only the ways they make it gets weird. But those are all number theories. If you study those things, they're going to help you find a state. More than anything, look at the definition is what I'll tell you. Can you apply that definition to anything right in front of you? Well, then it should be able to apply to that number theory. I'd be glad you understood it, because not that the number system itself will do you anything. It's more of a pattern or a logic system that those things help you develop. So while I'm in there, we're going to talk about a bunch of different ones. Not that you'll ever use any of them, but you'll talk about the form, and you'll talk about applying definitions and the given size and space and times that you need, because it's where and when you talk about prime systems to make this engine roll, to keep it going down the road, because your hand's on the wheel and your ass is in the seat. You could say that's the matrix ones and zeros. It's all relative to all of those numbers and whatever organization they come off to be the super unified field theory like Hawking's is talking about, and all black hole calculations. They're all just number theory at the end of the day, until you apply it in quantum gravities. This conversation, direct physics. Okay, highly composite systems, which we kind of covered. Riemann's hypothesis, which has to do with finding patterns in prime numbers, which I actually found a few, but we'll talk about that later, seeing that's a very valuable equation. But what I was talking about before is usually my course lecture to define something practical or applied that you can do with it. Poincare's conjecture, which is more like an air turbulence equation. You have a stone dock and a customer. They look like two different. They are two different universes. When I'm a buyer, I'm not a seller. Where they meet in the middle are where those, I forget what they're called. You know, those two little systems where this is one thing, this is the other, this is what they have in common. Well, they work like air molecules, right? And they're flowing into a real system. And when that changes, it's always moving, it's applying to the laws of motion, but they pass through each other to a certain way in a Lorentzo's mathematics equation to describe exactly what you're looking at. And that's going to come with a given specific general relativity to how you lay that all out in this second at this time to this conversation, which applies to other stuff. But remember, if you only do one of them, it's like, well, let's destroy the whole world because I don't care about the laws of motion or generals or the art of war or anything like that. Fuck it, we don't need it. We can get it through other models. Fuck them all. Well, it doesn't work that way. They're studied, they're practiced, people use them, courses in colleges teach this stuff, so either I'm going to burn them all down and tell them to teach my stuff and take over, or I'm just going to be like, well, we can use those models. They can be very productive in a system. We can do those things this way. Instead of just being stone dock, fuck it, we're all growing corn today, because it's a dictatorship, not a democracy, really, let's face it. Yeah, give me that shit all day. No, I'm just working with you. And my last three are may not be in order after the first five. And again, that's the general model, because those five will help you understand all these other ones. It'll be a piece of something, a particle of that Big Bang once it goes critical mass. And may not be complete. You know, you can go way more into this. You got all kinds of math equations, all kinds of science equations, chemistry, business economics, business physics, you know, whatever for your given company. You can make this just about a company. I could make this just about all the relative features in Johnson Roads, or any given stone dock, or any factory, or multiple factories of different conversations, or landscaping, like I did my first one. Did landscaping, carpentry, plumbing, stone docks. I had a little bit of everything, and it evolved in that model to each teach you one frame, like a resume. That's a big bang. When you think about it mathematically of what's going on in there, really mathematically break down those terms that they say they could do in their job details. What real physics goes into that? We just generalized it. If you can make that quantum leap anyways, not everybody can. Form system may be relative to term used, therefore, an example for the engineering system, it would be more practical to use terms applied to engineering instead to universal systems. Referred this to quantum physics and relativity. So what I was talking about there, whether it be a full stone dock or what have you, and a lot of those other ones. Now I actually start to break down each of these. Phase equation, general relativity equations. Well, I had to do a first part of the phase equation, which is a piece of general relativity. Erodes, Fermat's, Beals, Young's mass gap, NP problem, Hodge's conjecture. Which, just real quickly again, I want to read you Young's mass gap. The laws of quantum physics stand to the world of elementary particles in the way Newton's law of classical mechanics to the microscopic world. Almost half the century ago, Young's mass introduced a remarkable new framework, stone deck, to describe elementary particles. Think about that for a second. Using structures that also occur in geometry. Well, we're just saying that dimensions are the structural engineering here. And this is a big Mason game right here, and it's not just that I'm quoting that stuff. It's my specific model through it, as general of elementary theory, and it's predictions have been tested at many experimental laboratories, but its mathematical foundation is still unclear. Very hard equation to very well lay out and say a Stonedock's math numbers. If I laid it all out, well, that's the Big Bang Theory. It's a tough sell. To successfully using Seal's mass theory and strong interactions of elements, particles depend on a subtle quantum mechanics property. So I'm running out of time. Catch you on the next one.